Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Now, I want you to imagine something absolutely impossible. Picture this. You wake up tomorrow morning, grab your coffee, and check the news like any other day. But the headlines aren't about politics or celebrities. Every single news channel, every website, every social media feed is showing the same unbelievable footage. The ocean, our familiar, murky, green-grey ocean, has turned crystal clear overnight. I'm not talking about that beautiful Caribbean blue you see in vacation photos. I mean crystal clear, pristine, like looking through the purest mountain lake you've ever seen, except it stretches to the horizon in every direction. The water is so transparent that fishing boats are reporting they can see the ocean floor at depths of 200 feet. Swimmers in California are panicking because they can suddenly see exactly how deep the water goes beneath them. But here's the thing, and this is where it gets really wild. This isn't just about the water looking different. Something fundamental has changed. Every grain of salt, every dissolved mineral, every trace element that makes seawater what it is has simply vanished. Overnight, Earth's oceans have become freshwater. Think about that for a second. We're talking about 321 million cubic miles of water that has been salty for 4 billion years suddenly becoming as fresh as the water flowing from your kitchen tap. The ramifications are so massive, so immediate, and so catastrophic that it's almost impossible to wrap your head around. Within hours, the first signs of disaster begin appearing along coastlines worldwide. Marine biologists are the first to understand what's happening, and they're absolutely horrified. You see, ocean fish have spent millions of years evolving to live in salt water. Their entire biological system depends on that precise balance of minerals. When you suddenly remove the salt, their cells start absorbing water at a deadly rate. Picture a salmon trying to swim in this new freshwater ocean. Its body, perfectly designed to extract water from a salty environment, suddenly can't regulate the flow. Water rushes into its cells faster than they can handle it. The fish literally begins to swell. Within minutes, cell walls start bursting from the pressure. It's like inflating a balloon until it pops, except it's happening to every cell in the fish's body simultaneously. The death toll is immediate and staggering. Tuna, cod, mackerel, anchovies, sea myrrh, species that have thrived in the ocean for millions of years, are dying by the billions. The water near every coastline starts turning a horrific shade of brown as fish carcasses float to the surface. Commercial fishing boats that went out expecting a normal day's work are returning with holds full of dead fish, their crews pale and shaken by what they've witnessed. But the fish are just the beginning. Marine mammals are facing their own nightmare scenario. Whales and dolphins rely on echolocation to navigate. They send out sound waves and listen for the echoes to build a mental map of their surroundings. But here's what's crazy. Saltwater and freshwater have completely different acoustic properties. The sound waves that worked perfectly in the ocean's salty environment are now behaving totally differently. Imagine being in a familiar room when suddenly all the furniture is rearranged, except you're blind and navigating by sound alone. That's what every whale and dolphin in the ocean is experiencing right now. Their sonar is essentially useless. Pod after pod of these magnificent creatures are beaching themselves along coastlines, their navigation systems completely scrambled by the change in water density. The scene in coastal cities is becoming increasingly surreal. In Boston Harbor, dock workers are staring in disbelief as the water around the piers begins to freeze. You heard that right. Freezing. Saltwater freezes at about 28.4 degrees Fahrenheit, but freshwater freezes at 32 degrees. In harbors around the world where the temperature hovers around 30 degrees, ice is forming for the first time in recorded history. Ships that were perfectly fine yesterday are now trapped in unexpected ice sheets. The port of Rotterdam, normally bustling with cargo vessels, looks like an Arctic landscape. Captains are radioing for icebreakers in waters that have never needed them before. The global shipping industry, the backbone of international trade, EDA, grinds to a halt as ports from Norway to New England become inaccessible. But wait, there's more. And this is where the story gets really fascinating from a scientific perspective. You see, we're not just watching a disaster unfold, we're witnessing the unraveling of 4 billion years of planetary evolution in real time. Every system on Earth that depends on the ocean's salinity is failing simultaneously, and it's giving us an incredible window into just how interconnected our planet really is. The Gulf Stream, that massive river of warm water that flows from the Caribbean up the eastern coast of North America and across to Europe, simply stops. Most people don't realize that this current isn't driven by wind or tides. It's powered by differences in water density. Salty water is heavier than fresh water, and as the Gulf Stream reaches the cold North Atlantic, it becomes even denser and sinks to the ocean floor, creating a conveyor belt effect that keeps the current flowing. Without salt, that density difference disappears. The Gulf Stream, which has been flowing for millions of years, shudders to a halt like a massive engine running out of fuel. The implications are staggering. London, which sits at the same latitude as Labrador in Canada, depends entirely on Gulf Stream warmth to maintain its moderate climate. Within weeks, temperatures in Western Europe begin plummeting toward levels not seen since the last ice age. Meanwhile, the Caribbean and southeastern United States, no longer cooled by the Gulf Stream's circulation, start experiencing brutal heat waves. It's as if someone has shut off the planet's air conditioning system. The delicate balance that has kept Earth's climate stable for millennia is collapsing. Ocean currents around the world are experiencing similar disruptions. The Kuroshio Current off Japan weakens dramatically. The California Current changes direction entirely. Weather patterns that have remained consistent for thousands of years become chaotic and unpredictable. Meteorologists are throwing up their hands. Their models, based on decades of data from a salty ocean world, are completely useless. And here's something that will blow your mind. The absence of salt is affecting the ocean's ability to hold heat. Salt water has a higher specific heat capacity than fresh water, meaning it can absorb and store more thermal energy. Our freshwater oceans can't regulate temperature the way they used to. The planet's most important climate stabilizer has suddenly become unreliable. But perhaps the most unsettling discovery comes from marine chemists studying water samples. They're finding that the ocean's pH levels are fluctuating wildly. You see, dissolved salts act as buffers, helping maintain the slightly alkaline conditions that ocean life requires. Without these minerals, the water's chemistry becomes unstable. Some areas are becoming dangerously acidic, while others swing toward extreme alkalinity. It's chemical chaos on a planetary scale. Coral reefs, already stressed by climate change, face immediate extinction. These incredible ecosystems depend on calcium carbonate to build their limestone skeletons. But calcium carbonate can only precipitate properly in the presence of specific mineral concentrations. In fresh water, the chemistry simply doesn't work. The Great Barrier Reef, the world's largest living structure visible from space, begins dissolving almost immediately. The economic implications are staggering. The global fishing industry, worth over $200 billion annually, ceases to exist overnight. Coastal tourism collapses as beaches become graveyards for marine life. Shipping companies face billions in losses as ports become unusable. Salt production facilities around the world sit empty and useless. There's literally no salt left to harvest. But hidden in this apocalyptic scenario are clues to understanding something profound about our planet. As scientists scramble to comprehend what's happening, they're making discoveries about Earth's systems that would have taken decades to uncover under normal circumstances. We're seeing, in fast forward, just how fundamental those 35 parts per thousand of dissolved minerals really are. Every drop of ocean water contains a complex cocktail of elements. Sodium and chloride, of course, but also magnesium, sulfur, calcium, potassium, and traces of nearly every element on the periodic table. These aren't just random additions, they're the result of 4 billion years of planetary processing. Every underwater volcano, every river carrying minerals from weathered rocks, every grain of sediment settled on the seafloor has contributed to this precise chemical balance. The salt in our oceans isn't just seasoning, it's a record. A 4 billion-year-old library written in dissolved minerals, telling the story of our planet's transformation from a molten ball of rock to a world capable of supporting life. And now, in our impossible thought experiment, we're watching that entire history vanish in a single day. As rescue crews work around the clock to save stranded marine life and engineers struggle to reopen frozen ports, one thing becomes crystal clear. We've been taking the ocean's saltiness for granted. We've treated it as a simple fact of nature, like gravity or the speed of light. But this disaster is revealing that Earth's salty seas are actually an incredibly delicate achievement, H2O, the result of countless geological and chemical processes working in perfect harmony for billions of years. The first day of our freshwater world ends with humanity stunned and struggling to comprehend the magnitude of what has changed. But this is just the beginning. As we'll discover, removing salt from Earth's oceans doesn't just affect marine life and weather patterns. It rewrites the entire story of how our planet became habitable in the first place. And that story, Tuonel, the incredible journey from Earth's first freshwater oceans to the salty seas that made complex life possible, is where we're heading next. But here's what's absolutely mind-blowing. Earth's oceans weren't always salty. 4 billion years ago, when our planet was still a hellish landscape of molten rock and toxic gases, the first oceans formed from something that might surprise you: completely fresh water. Picture this incredible scene. You're standing on the early Earth, though you'd die instantly from the poisonous atmosphere, watching the planet's surface cool for the first time in millions of years. The temperature has finally dropped below 212 degrees Fahrenheit, the boiling point of water. For the first time in Earth's violent history, water vapor can condense into liquid. And here's the crazy part. It falls as pure, fresh rainwater. For millions of years, massive storms dump freshwater rain onto the cooling surface. No salt, no minerals, just H2O in its simplest form. These first oceans are essentially giant freshwater lakes covering most of the planet. If you could somehow taste this ancient water, it would be purer than anything you've ever experienced, cleaner than distilled water, cleaner than the purest mountain spring. So how did we get from those pristine freshwater seas to the complex mineral-rich oceans we know today? The answer is one of the most dramatic transformation stories in planetary history, and it took over 1 billion years to unfold. The Great Salting, as scientists call it, began with violence. Underwater volcanoes, seasoned O, and I mean massive, continent-sized volcanic systems, started pumping chemicals into those pristine seas. We're talking about eruptions that make modern volcanoes look like birthday candles. These weren't just spewing lava, they were injecting enormous quantities of dissolved gases and minerals directly into the ocean. Let me give you some numbers that will blow your mind. Every single year during this period, underwater volcanic activity was releasing approximately 27 million tons of chlorine gas into the water. 27 million tons. That's roughly equivalent to the weight of 200 Empire State Buildings worth of chlorine being dissolved into the ocean annually, year after year, for hundreds of millions of years. But chlorine was just one player in this chemical symphony. These volcanic systems were also bleeding massive amounts of sodium, magnesium, sulfur, and dozens of other elements into the water. Think of each underwater volcano as a giant chemistry set, mixing and dissolving elements that had been locked away in Earth's crust since the planet formed. Meanwhile, on the surface, an equally dramatic process was taking place. The continents, still young and geologically active, were literally dissolving. Rivers, carrying acid rain from that toxic early atmosphere, were carving through mountains and plains, dissolving rocks and carrying their mineral contents to the sea. Here's where it gets really fascinating. The process wasn't random, it was selective. Different minerals dissolve at different rates and in different conditions. Sodium and chloride, the main components of table salt, happen to be incredibly soluble and stable in water. Once they entered the ocean, they stayed there. Other elements, like iron and aluminum, would precipitate out and settle to the seafloor. Over millions of years, this process acted like a massive filtration system. The ocean became a chemical accumulator, collecting and concentrating the most stable water-soluble minerals while filtering out everything else. It's as if the entire planet became a laboratory dedicated to creating the perfect chemical recipe for life. Now, you might be wondering, when exactly did scientists figure this out? The story of discovering the ocean's salty origins is almost as fascinating as the process itself. It starts with a French chemist named Antoine Lavoisier in the 1700s. Lavoisier, who's famous for discovering that water is made of hydrogen and oxygen, became obsessed with understanding what else was dissolved in seawater. Using primitive but ingenious techniques, Lavoisier evaporated gallon after gallon of seawater, carefully weighing and analyzing the residue. He was the first person to systematically catalogue the ocean's chemical composition. His work revealed that seawater contained not just salt, but a complex mixture of dissolved minerals in remarkably consistent proportions. But Lavoisier couldn't answer the big question. Where did all this salt come from? That mystery would take another 2 centuries to solve. The breakthrough came in the 1960s and 70s with deep-sea drilling projects. Scientists developed technology to extract core samples from the ocean floor, essentially drilling backwards through time. These cores contained layers of sediment and salt crystals that had been accumulating for millions of years. What they found was revolutionary. The deeper they drilled, the fresher the ancient seawater became. They could literally trace the ocean's increasing salinity through geological time. Salt crystals trapped in these ancient sediments told the story of gradual chemical accumulation spanning billions of years. One of the most exciting discoveries came from analyzing salt deposits that formed when ancient seas evaporated. These deposits, found in places like the Dead Sea region and parts of the American Southwest, contained chemical fingerprints that revealed the composition of ancient oceans. Scientists realized they were looking at snapshots of the ocean's chemical evolution, preserved in solid form. The picture that emerged was stunning. About 3.8 billion years ago, Earth's oceans reached a critical threshold. The salt concentration had built up enough to fundamentally change how chemistry worked in the water. This wasn't just about taste or density. It was about enabling entirely new types of chemical reactions that simply couldn't happen in fresh water. Here's what's wild about this timing. 3.8 billion years ago is also when we start seeing the first evidence of complex chemical processes that might have led to life. Coincidence? Absolutely not. The increasing salinity of Earth's oceans created the chemical conditions necessary for the organic molecules that would eventually become the building blocks of life. Salt water can dissolve and stabilize complex organic compounds that would break apart in fresh water. It can facilitate chemical reactions between different molecules that wouldn't interact in a pure water environment. Most importantly, it creates the kind of chemical gradients and concentrations that allow for the formation of cell membranes, ADE, the fundamental boundary between living and non-living matter. But the Great Salting wasn't a smooth, gradual process. There were dramatic fluctuations, periods when volcanic activity increased or decreased, times when massive asteroid impacts temporarily boiled away parts of the ocean, resetting the chemical clock. Each of these events left its signature in the geological record. One of the most significant events happened about 2.5 billion years ago during what scientists call the Great Oxidation Event. As the first photosynthetic organisms began producing oxygen, it reacted with dissolved iron in the ocean, causing massive precipitation events. For millions of years, the ocean turned rust-colored as iron oxide settled to the seafloor. These iron formations, still visible today in places like Australia's Pilbara region, represent one of the most dramatic chemical transitions in ocean history. The salting process also explains some puzzling features of our planet. Ever wonder why certain inland areas, like the Great Salt Lake or the Dead Sea, are incredibly salty? These are remnants of ancient ocean basins that were cut off from the main ocean system. As water evaporated over millions of years, the salt concentration increased far beyond normal seawater levels. They're like time capsules, preserving snapshots of the ocean's chemical evolution. Modern technology has allowed scientists to reconstruct this process with incredible precision. Sophisticated computer models can simulate the gradual chemical evolution of Earth's oceans, tracking how different elements accumulated over geological time. These models reveal that the process was far more complex than simple accumulation, AST. There were feedback loops, tipping points, and chemical cascades that shaped the final composition. What's really remarkable is how precisely balanced the final result turned out to be. The concentration of salt in modern seawater, ABPP, about 35 parts per thousand, represents an almost perfect equilibrium. It's concentrated enough to enable complex chemistry and life processes, but not so salty that it becomes toxic to most organisms. If the concentration were significantly higher or lower, life as we know it probably couldn't exist. Recent discoveries have made this story even more intriguing. Scientists studying underwater volcanic vents have found that these systems are still actively contributing to ocean chemistry. The famous black smokers, underwater vents that spew superheated, mineral-rich water, are modern examples of the same processes that salted our oceans billions of years ago. These vents support unique ecosystems of creatures that thrive in extremely salty, mineral-rich water. They're like living laboratories, showing us how life might have first adapted to increasingly salty oceans. Some researchers believe these vent systems might be modern analogues for the conditions where life first emerged on Earth. The implications go far beyond Earth's history. As we search for life on other planets, understanding how our oceans became salty gives us crucial insights into what to look for. Mars, for example, shows evidence of ancient seas that might have gone through their own salting process. Europa, one of Jupiter's moons, has a subsurface ocean that might be actively accumulating minerals from its rocky core. The story of Earth's salty oceans is really the story of our planet becoming habitable. Without that billion-year process of chemical accumulation, the complex chemistry that makes life possible simply couldn't exist. Every grain of salt in seawater represents millions of years of planetary evolution, a testament to the incredible geological processes that transformed a hellish young world into the life-supporting planet we know today. But here's the thing that really gets me excited about this story. We're still discovering new chapters. Just last year, scientists found evidence of ancient salt deposits that suggest the salting process might have happened in multiple phases, with periods of chemical reset that we never knew about. The ocean's chemical history is still being written, and we're still learning to read it. This brings us to a fascinating question. If Earth's oceans started fresh and gradually became salty, what would have happened to life if they had stayed fresh? How would evolution have unfolded in a world of freshwater seas? The answer to that question takes us into one of the most mind-bending thought experiments in planetary science. Now here's where our story takes a completely wild turn. Imagine if Earth's oceans had never become salty. Picture evolution taking a fundamentally different path for the past 4 billion years. What we're about to explore isn't just speculation, It's based on cutting-edge research into how salinity shapes life at the most basic cellular level. In our freshwater world, the first and most dramatic change would be the complete absence of osmotic pressure challenges. Now, I know that sounds technical, but stick with me because this is absolutely crucial to understanding how different life would be. Every cell in every ocean creature today is essentially a tiny water management system. Fish, for example, have to constantly work to maintain the right balance of water and salt in their bodies. A saltwater fish is actually losing water to its environment all the time because the ocean is saltier than its body fluids. To survive, it has to drink seawater constantly and pump out the excess salt through specialized glands. But here's what's fascinating. In our freshwater ocean, this biological arms race never happens. Cells don't need complex mechanisms to regulate water flow because there's no osmotic pressure to fight against. This might sound like it would make life easier, but it actually opens up possibilities that are almost impossible to imagine. Without osmotic constraints, organisms can grow much larger than anything we see in today's oceans. Think about it. One of the major limiting factors for size in marine life is the energy cost of managing water balance. Remove that constraint, and you remove one of evolution's biggest size limits. Picture this. Freshwater squid, the size of modern blue whales. We're talking about cephalopods with 100-foot tentacles, intelligence comparable to dolphins, but with the massive scale that only freshwater allows. Their nervous systems, freed from the constant energy drain of osmotic regulation, could develop incredible complexity. But it's not just about size. The absence of salt fundamentally changes how evolution approaches the problem of survival. In our world, marine animals developed incredible specializations to deal with salt water. Sharks have these amazing organs called rectal glands that can process enormous amounts of salt. Bony fish evolved kidneys that can concentrate urine to incredible levels while extracting every drop of fresh water from seawater. None of these adaptations exist in our freshwater world. Instead, evolution channeled all that creative energy into entirely different directions. Imagine whale-sized salamanders with skin so permeable they can absorb oxygen directly from water across their entire body surface. Picture fish with internal air bladders the size of small rooms, allowing them to achieve neutral buoyancy that's impossible in today's oceans. The reproductive strategies would be completely different too. Many marine animals today release millions of eggs because saltwater is such a harsh environment for developing embryos. In freshwater oceans, embryonic development could be far more protected and efficient. Fish might evolve to have fewer, larger offspring with much higher survival rates. But here's where it gets really wild. Coral reefs never form. The entire ecosystem that we associate with tropical oceans simply can't exist. Coral animals build their limestone skeletons using calcium carbonate, but this process only works efficiently in saltwater, with specific mineral concentrations. In fresh water, the chemistry just doesn't add up. Now, you might think this means less biodiversity, but nature abhors a vacuum. In place of coral reefs, imagine vast underwater forests of giant freshwater kelp, extending from the poles to the equator. These aren't the kelp forests we know from cold waters. We're talking about tropical freshwater kelp that could grow to incredible heights without the buoyancy limitations of saltwater. These kelp megaforests would support entirely different ecosystems. Instead of colorful reef fish, picture schools of iridescent freshwater species that have evolved complex social behaviors around these underwater trees. Imagine freshwater equivalent of sea turtles, 2,000 higher, perhaps giant salamander-like creatures with shells, grazing on kelp leaves the size of dinner tables. The lack of calcium carbonate precipitation means no limestone formation, which completely changes the ocean floor geology. Instead of coral atolls and limestone cliffs, the seafloor would be dominated by massive sediment plains and volcanic formations. This changes everything about ocean chemistry, current patterns, and nutrient distribution. Here's something that will blow your mind. The Cambrian explosion, that incredible period 540 million years ago when complex life forms suddenly appeared in the fossil record, probably never happens, at least not the way we know it. The Cambrian explosion was triggered partly by the development of hard shells and exoskeletons, which require specific mineral concentrations to form efficiently. In freshwater oceans, that evolutionary pressure doesn't exist. Instead of the sudden appearance of shelled creatures, evolution might have taken a completely different approach to protection and structure. Perhaps we'd see the rise of creatures with incredibly tough, flexible exoskeletons made from organic polymers rather than calcium carbonate. The food webs would be fundamentally different too. Today's ocean food chains depend heavily on tiny organisms called foraminifera and coccolithophores, AG, microscopic creatures that build calcium carbonate shells. These organisms form the base of many marine food webs and are crucial for carbon cycling. In freshwater oceans, entirely different microscopic organisms would fill these niches. Without shell-building plankton, the ocean's ability to sequester carbon would work through completely different mechanisms. Perhaps massive blooms of freshwater algae would dominate, creating seasonal cycles of carbon absorption and release that don't exist in our salty seas. The evolution of intelligence would likely follow different pathways too. Today's marine mammals, whales, dolphins, and seals, evolved from land animals that returned to the sea. But in a freshwater ocean world, the transition from land to sea would be much easier. We might see entire lineages of intelligent creatures that never fully committed to either environment, remaining amphibious and developing technologies that work both underwater and on land. Think about communication. Whales and dolphins use echolocation, partly because vision is limited in salty, often murky seawater. In crystal-clear freshwater oceans, visual communication might dominate. Imagine schools of intelligent fish with complex visual languages, using color patterns and bioluminescence to communicate across vast distances in ways that would be impossible in today's oceans. The absence of tides would also reshape evolution dramatically. Tidal zones, those incredibly biodiverse areas where land meets sea, are crucially dependent on saltwater density and its interaction with gravitational forces. In freshwater oceans, tidal effects would be much weaker, and the intertidal zone, one of evolution's most creative laboratories, would barely exist. This means no barnacles, no tidal pool ecosystems, no creatures adapted to the rhythm of tides. Instead, evolution might have focused on deeper water environments, creating incredible diversity in the abyssal zones that remain largely unexplored in our world. Here's something particularly fascinating. Without salt's preservative properties, the ocean's ability to maintain organic compounds would be dramatically different. This could actually accelerate certain evolutionary processes while slowing others. Complex organic molecules, they might break down faster, but they might also form and experiment with new combinations more readily. The symbiotic relationships that define so much of marine life would be completely different. Today's coral polyps depend on symbiotic algae that can handle saltwater conditions. In freshwater, entirely different partnerships would evolve. Perhaps massive filter-feeding animals would develop symbiotic relationships with freshwater photosynthetic organisms, creating living reefs made of flesh and plant matter rather than limestone. Migration patterns would be utterly transformed. Many marine animals today migrate based on salinity gradients and temperature differences that are maintained by salt's effects on water density. Without these gradients, migration might be driven by completely different factors, perhaps following nutrient blooms or seasonal changes in freshwater plankton populations. The deep ocean would be a completely different world. Today's deep-sea creatures often depend on marine snow, a constant rain of organic matter from surface waters that's partly maintained by saltwater's chemical properties. In freshwater oceans, this entire system would work differently. possibly creating much more dynamic and nutrient-rich deep ocean environments. But here's what really gets me excited about this thought experiment. Recent discoveries in freshwater environments suggest that some of these adaptations might actually be possible. Scientists have found freshwater organisms in deep underground lakes that show incredible diversity and specialization. Lake Baikal in Siberia, the world's oldest and deepest freshwater lake, has evolved species found nowhere else on Earth. These discoveries suggest that freshwater environments can support incredible biodiversity when given enough time and space. Scale that up to entire oceans over billions of years, and the possibilities become almost unlimited. The absence of salt would even change how we think about the bow, the origin of life itself. Many theories about life's beginning depend on the chemical properties of salt water to concentrate and stabilize the first organic molecules. In a freshwater world, life might have originated through completely different chemical pathways, possibly creating fundamentally different types of biology from the very beginning. What we're really talking about is not just different species, but potentially different kingdoms of life entirely. The basic biochemistry that evolved in saltwater oceans shaped everything about how life works on Earth. In freshwater oceans, evolution might have discovered completely different solutions to the basic problems of existence, energy, and reproduction. This brings us to an even more mind-bending possibility. Who known before? What if this alternate evolution had created intelligent life forms that developed technology and civilization? How would their entire understanding of chemistry, physics, and planetary science be different? Would they even recognize our salty Earth as a potentially habitable world? But our thought experiment is just getting started, because changing the ocean's chemistry doesn't just affect life, it completely transforms the planet's weather systems, and that's where things get really crazy. Now we're getting to the part of our story that literally reshapes the entire planet. Because here's the thing about removing salt from Earth's oceans, you're not just changing marine biology or ocean chemistry, you're fundamentally altering the physics of how our planet works. And it all starts with a temperature difference that seems almost insignificant, just 3.6 degrees Fahrenheit. Salt water freezes at 28.4 degrees Fahrenheit. Freshwater freezes at exactly 32 degrees. That tiny difference triggers the most massive climate transformation in Earth's history. Picture the Arctic Ocean during our planet's freshwater transformation. What is normally a delicate balance between freezing and melting suddenly tips dramatically toward ice. In regions where seawater barely stays liquid during winter months, freshwater begins freezing solid. We're not talking about a little more sea ice. We're talking about permanent ice sheets extending hundreds of miles further south than anything in recorded history. The polar ice caps don't just grow, they explode in size. Within a decade, the Arctic ice sheet triples in area. The Antarctic ice shelf extends so far north that icebergs become common sights off the coasts of Chile and New Zealand. This massive increase in white reflective ice surface triggers what scientists call the albedo effect on steroids. Here's how the albedo effect works. Dark surfaces like open ocean absorb solar energy and warm up. Light surfaces like ice and snow reflect that energy back to space. Normally, Earth maintains a careful balance between absorption and reflection, but when you suddenly triple the amount of reflective ice surface, you're essentially installing giant mirrors across the planet's polar regions. The result is catastrophic cooling. Average global temperatures begin dropping, not gradually, but in dramatic steps. Computer models suggest that within 50 years, Earth would enter the most severe ice age in its history. Glaciers would advance from both poles simultaneously, eventually meeting somewhere around what we now call the temperate zones. But the real drama happens with ocean currents, and this is where our story gets truly wild. Remember the Gulf Stream? That massive river of warm water that keeps Europe habitable? It doesn't just weaken when you remove salt from the oceans, it completely shuts down. You see, the Gulf Stream isn't powered by wind or tides. It's driven by differences in water density. Warm, salty water flows north from the Caribbean. As it reaches the cold North Atlantic, it becomes denser, both from cooling and from its high salt content, and sinks to the ocean floor. This sinking action pulls more warm water northward, creating a conveyor belt effect that moves more water than all the world's rivers combined. Remove the salt, and this density difference disappears. The Gulf Stream, which has been flowing for millions of years, simply stops. It's like someone pulled the plug on the planet's largest heating system. The consequences are immediate and devastating. London, which sits at the same latitude as southern Alaska, depends entirely on Gulf Stream warmth to maintain its temperate climate. Without it, Britain's climate shifts to resemble northern Canada within a matter of years. Vineyards in France freeze solid. Crops throughout northern Europe fail catastrophically. But here's the crazy part. While Europe freezes, other parts of the world begin cooking. The Gulf Stream doesn't just carry warm water north, it also carries away excess heat from the tropics. Without this massive heat transport system, the Caribbean and southeastern United States experience unprecedented warming. We're talking about temperature increases that make current climate change projections look mild. Hurricane formation gets completely disrupted, but not in the way you might expect. Modern hurricanes depend on a complex interaction between warm surface water and cooler upper atmosphere. They also rely on saltwater's specific heat capacity, amine energy, its ability to store and release thermal energy gradually. Freshwater has a lower specific heat capacity than saltwater, meaning it heats up faster and cools down more quickly. This creates much more volatile temperature gradients in the atmosphere above our freshwater oceans. The result? Either no hurricanes at all in some regions, or hypercanes, massive storm systems with wind speeds that dwarf anything in recorded history. Imagine storm systems with sustained winds of 500 miles per hour, covering areas the size of Texas. These aren't hurricanes as we know them. They're weather phenomena that have no equivalent in our current climate system. The energy that normally gets distributed gradually through ocean currents, instead, gets concentrated into these massive atmospheric disturbances. The monsoon systems that billions of people depend on for agriculture completely collapse. Monsoons are driven by seasonal temperature differences between land and ocean, but these differences depend on saltwater's thermal properties. In our freshwater world, the delicate balance that brings life-giving rains to India, Southeast Asia, and parts of Africa simply ceases to exist. Without monsoons, the Ganges River slows to a trickle. The rice paddies that feed over 1 billion people turn to dust. The Sahara Desert, normally held in check by Atlantic moisture patterns, begins expanding eastward at an unprecedented rate. But wait, here's where it gets really strange. While some deserts expand dramatically, others completely disappear. The Atacama Desert in Chile, normally one of the driest places on Earth, begins receiving regular rainfall for the first time in millions of years. Why? Because the ocean current patterns that normally divert moisture away from the Atacama have been completely disrupted. Weather prediction becomes essentially impossible. All of our meteorological models are based on decades of data from a planet with salty oceans and stable current patterns. In our freshwater world, the butterfly effect gets amplified beyond anything scientists have ever observed. A temperature change in one part of the ocean can trigger completely unpredictable weather patterns on the opposite side of the planet weeks later. Let me walk you through what happens to a single water molecule in this chaotic new system. In our normal world, a water molecule evaporating from the tropical Atlantic might follow a predictable path, carried by trade winds, condensing into clouds, eventually falling as rain in the Amazon rainforest, flowing back to the ocean through rivers, and then getting caught up in the Gulf Stream to repeat the cycle. In our freshwater world, that same molecule's journey becomes completely unpredictable. Without the Gulf Stream to guide it, Without stable temperature gradients to create reliable wind patterns, it might end up anywhere. It could evaporate from the tropical Atlantic and end up as snow in the Sahara Desert, or as rain in Antarctica. This chaos extends to regional weather patterns that have remained stable for thousands of years. The jet stream, that high-altitude river of air that guides weather systems across continents, becomes wildly unstable. Without the thermal anchoring provided by consistent ocean temperatures, the jet stream begins meandering in unprecedented ways. Winter storms that normally track across the northern United States instead dive deep into Mexico. Heat waves that should stay in the desert southwest end up in Alaska. The reliable seasonal patterns that agriculture depends on become completely random. El Niño and La Niña, those cyclical changes in Pacific Ocean temperatures that affect weather worldwide, have ceased to exist. These phenomena depend on specific interactions between ocean temperature, salinity, and current patterns. In our freshwater Pacific, entirely new and unpredictable oscillations take their place. The Amazon rainforest, which depends on moisture transported from the Atlantic Ocean, begins dying within decades. The intricate system that recycles water through the rainforest canopy breaks down as Atlantic moisture patterns become chaotic. What was once the planet's largest rainforest starts transforming into savanna, then grassland, then desert. Meanwhile, the Sahara Desert begins receiving so much moisture from disrupted Atlantic patterns that it turns green for the first time in millions of years. Imagine vast grasslands where sand dunes once stood, rivers flowing where there has been nothing but rock and sand for millennia. The seasonal cycle itself becomes unreliable. Winters in some regions last for years, while other areas experience permanent summer conditions. The delicate timing that migrating animals depend on, when to travel, when to breed, when to hibernate, becomes completely scrambled. But perhaps the most unsettling change is what happens to regional microclimates. Coastal areas that have enjoyed moderate temperatures for thousands of years suddenly experience continental climate extremes. Islands in the middle of the ocean, formerly blessed with stable maritime weather, begin experiencing the wild temperature swings of landlocked deserts. The Great Lakes region provides a fascinating example of how these changes cascade. Normally, these massive freshwater bodies are surrounded by salty oceans that moderate their climate. But in our freshwater world, the thermal buffering effect of the surrounding oceans disappears. The Great Lakes region experiences temperature swings that rival those of central Siberia. Mountain weather patterns become completely unpredictable. Ranges like the Rockies and the Alps normally create reliable rain shadows and wind patterns based on their interaction with moisture-carrying ocean winds. But when ocean moisture patterns become chaotic, mountain weather turns chaotic too. Ski resorts in Colorado might receive 30 feet of snow one year and none the next. The timing of these changes makes them even more devastating. Unlike gradual climate change that allows some adaptation, the collapse of salt-driven ocean systems happens within decades. There's no time for ecosystems to adapt, no time for human agriculture to adjust, no time for infrastructure to be redesigned for new weather patterns. What we're really witnessing is the breakdown of the fundamental systems that have kept Earth's climate stable for millions of years. The ocean-atmosphere heat exchange that moderates our planet's temperature, the current systems that distribute thermal energy globally, the precipitation patterns that support life on land, what of these, depend on the specific properties of saltwater. But our freshwater Earth's climate chaos is just the beginning. Because when you change the fundamental physics of how the planet works, you don't just alter weather patterns, you completely rewrite the story of human civilization itself. And that's where our thought experiment takes its most dramatic turn yet. Now here's where our story gets absolutely fascinating, because we're about to explore how every single human civilization would have developed completely differently in a world of freshwater oceans. I'm talking about a complete rewrite of human history, starting with the very first settlements along ancient coastlines. Let's begin with something as simple as the color purple. In our world, purple became the color of royalty and wealth because of tiny sea snails called murex. These creatures, found in the salty Mediterranean, produce a purple dye so valuable that it was literally worth more than gold. The Phoenicians built their entire trading empire around this purple dye, establishing trade routes that connected the ancient world. But in our freshwater Mediterranean, murex snails never evolved. The complex biochemistry that produces their purple pigment requires specific saltwater conditions. Without purple dye, the entire concept of royal colors develops differently. Maybe royal families adorn themselves in brilliant reds from iron oxides or deep blues from freshwater algae. The Phoenicians never become the master traders of the ancient world. They become something entirely different. Actually, let's talk about the Phoenicians for a moment, because their story illustrates just how fundamentally different human development would be. These master seafarers didn't just trade purple dye, APA, they were the first people to preserve fish using salt. Massive salt works along the Mediterranean coast allowed them to create preserved fish that could last for definite months, enabling long-distance voyages and trade. In our freshwater world, there is no salt to harvest. No salt means no fish preservation, which means no long-distance maritime trade. The Phoenicians, if they exist at all, remain coastal fishermen using smoking and fermentation techniques to preserve their catch. They never develop writing systems to track complex trade relationships. They never establish colonies across the Mediterranean. The spread of alphabetic writing, HMIS, one of humanity's most crucial innovations, happens completely differently, if at all. This brings us to one of the most dramatic alternative histories, the Vikings. These master seafarers revolutionized shipbuilding partly because they needed vessels that could handle the harsh, salty North Atlantic. But here's what's really crucial. They preserved their food using salt, particularly their fish and meat, which allowed them to make voyages lasting months. In our freshwater world, food preservation is limited to smoking, drying, and fermentation. Viking longships, if they're developed at all, can only support much shorter voyages. They never reach Iceland, never establish settlements in Greenland, never make it to North America. The entire age of exploration gets pushed back by centuries because maritime food preservation is so limited. But the most dramatic change might be what happens to the British Empire. Britain's naval dominance was built on several factors that simply don't exist in a freshwater world. First, their ships lasted longer because saltwater corrosion wasn't constantly eating away at metal components. Second, they could preserve food for extended voyages. Third, and this is crucial, they understood how to navigate using ocean salinity layers and currents. In our freshwater world, wooden ships rot much faster in harbours because the natural antiseptic properties of salt are gone. Metal components last longer without salt corrosion, but wood, the primary shipbuilding material for most of history, becomes much more vulnerable to decay and marine organisms that thrive in fresh water. The British never developed their naval advantages. Spain, Portugal, and other Atlantic powers face the same limitations. The entire age of exploration unfolds at a much slower pace, if at all. Columbus never makes his voyage to the Americas because reliable ocean navigation techniques don't exist without saltwater density layers to guide ships. This means the indigenous peoples of the Americas continue developing their civilizations for centuries longer without European contact. The Aztec and Inca empires might have time to develop technologies and social systems that could have resisted European colonization entirely. Native American societies along the coasts developed their own unique approaches to freshwater maritime technology. Speaking of the Americas, the lack of salt creates fascinating alternative development paths. Many Native American societies traded extensively for salt, sometimes traveling hundreds of miles to reach salt springs or ocean evaporation sites. In our freshwater world, these trade networks never develop. Instead, Societies might organize around smoking and fermentation technologies, creating entirely different types of food preservation expertise. The Roman Empire faces its own unique challenges. Roman soldiers received part of their pay in salt. That's where we get the word salary. Without ocean salt works, the Romans never developed this payment system. More importantly, Roman road networks were partly designed to transport salt from coastal works to inland cities. In our freshwater world, these transportation networks develop around completely different resources. Instead of the famous Roman roads connecting salt works to cities, we might see networks designed to transport preserved foods from smoking centers, or paths connecting communities with the best fermentation technologies. The entire economic foundation of Grosmus, the Roman Empire, shifts from salt-based trade to something entirely different. But here's where it gets really interesting. The absence of salt-preserved foods means that armies can't march long distances or maintain extended sieges. Military campaigns that lasted years in our world become impossible when food spoils within days. The Roman Empire never expands beyond central Italy because their legions simply can't carry enough preserved food for extended campaigns. This limitation affects every major military power throughout history. Alexander the Great never conquers his vast empire because his armies can't maintain supply lines across thousands of miles without salt preservation. Genghis Khan's Mongol hordes remain regional powers because their mounted warfare depended heavily on preserved meat and dairy products that required salt. Medieval Europe develops along completely different lines. The Hanseatic League, that powerful confederation of merchant guilds that dominated northern European trade, was built largely on the saltfish trade. Baltic herring preserved in salt fed much of medieval Europe and created the wealth that funded everything from cathedrals to universities. In our freshwater world, the Hanseatic League never forms. Instead, regional confederations might develop around smoking technologies or fermentation expertise. Perhaps powerful guilds of smoke masters control trade routes, or confederations of cheesemakers dominate commerce through advanced fermentation techniques. The dietary differences alone would reshape entire cultures. Japanese cuisine, built around salted and fermented fish products, develops entirely different flavor profiles. Soy sauce, miso, and other fermented foods that depend on specific salt concentrations either don't exist or taste completely different. Japanese culture, so intimately connected to the sea and its bounty, evolves along fundamentally different paths. Mediterranean cultures face perhaps the biggest changes. The entire concept of Mediterranean cuisine, nine, olives, preserved in brine, salted fish, cheese aged in saltwater caves, simply doesn't exist. Instead, these cultures might become masters of oil preservation, developing sophisticated techniques for storing foods in olive oil or other fats. The spice trade that connected Europe and Asia would follow completely different routes and priorities. Without the need to mask the taste of salt-preserved foods, spices might be valued for entirely different properties. Instead of pepper and salt being the most valuable seasonings, perhaps fermentation enhancers or smoking spices become the basis of international commerce. Speaking of commerce, the entire concept of currency might develop differently. Many early civilizations used salt as a medium of exchange, i.e., it was valuable, portable, divisible, and didn't spoil. In our freshwater world, different materials become the basis of early monetary systems. Perhaps societies develop currencies based on dried fish, fermented grain products, or special smoking woods. The development of cities would follow different patterns too. In our world, many major cities developed at the mouths of rivers where fresh water met salt water, creating natural harbors and salt harvesting opportunities. Venice, built on salt works and maritime trade, never becomes a major power. Instead, it might remain a collection of fishing villages using freshwater preservation techniques. Coastal cities that depended on salt production, DSS, Places like San Francisco with its massive salt works, or Liverpool with its chemical industry built on salt processing, either side, develop entirely different economic foundations. These cities might become centers of smoking and fermentation technology, or they might never grow into major urban centers at all. The absence of iodine in the human diet creates one of the most significant health challenges in our alternative history. In our world, most people get iodine from seafood and salt from evaporated seawater. Iodine deficiency causes severe developmental problems, including intellectual disabilities and physical deformities. In our freshwater world, coastal populations don't get iodine from their diet unless they discover terrestrial sources like certain seaweeds or mineral deposits. This could lead to widespread developmental delays in coastal populations, fundamentally altering which societies develop advanced technologies and complex civilizations. Inland societies that discover iodine-rich mineral springs or certain plants might actually have significant advantages over coastal peoples. This could completely reverse the normal pattern of coastal civilizations, leading technological development. The development of chemistry and science takes different paths too. Many fundamental discoveries in chemistry came from studying salt and saltwater, the properties of acids and bases, the principles of crystallization, the basics of electrochemistry, all of these were first understood through experiments with salt. Without readily available salt, chemistry develops more slowly and along different experimental lines. Perhaps the science of fermentation advances much more rapidly, leading to earlier discoveries in biology and biochemistry. Or maybe the study of combustion and smoking leads to earlier advances in understanding gases and combustion chemistry. Navigation techniques evolve completely differently. In our world, sailors learn to read ocean currents, partly by understanding salinity differences. They could taste seawater and know roughly where they were based on salt content. Dead reckoning techniques use saltwater density as one factor in calculating position. In freshwater oceans, entirely different navigation methods develop. Perhaps sailors become expert at reading water temperature variations, or they develop sophisticated understanding of freshwater current patterns based on different principles. Maybe navigation advances more slowly, keeping civilizations more regionally isolated for longer periods. The development of metallurgy follows different paths because saltwater corrosion was a major driver of innovation in metal alloys and protective coatings. Without this challenge, certain metallurgical advances happen much later, while others that aren't relevant to salt corrosion might advance more quickly. Architecture evolves differently too. Coastal buildings in our world are designed to withstand salt air corrosion. In freshwater coastal areas, different environmental challenges shape building techniques. Perhaps the focus shifts to protecting against different types of moisture damage, or dealing with the unique challenges of freshwater marine environments. The entire timeline of technological development gets scrambled. Innovations that seemed natural and inevitable in our salt ocean world happen centuries later, or not at all, while technologies we never developed because we didn't need them become crucial for survival and advancement. But perhaps the most fascinating difference is how societies organize themselves around different preservation and storage technologies. Instead of salt-based trading empires, we might see the rise of massive smoking cooperatives, fermentation federations, or oil preservation partnerships. Imagine guild systems organized around different preservation techniques. FUA, master smokers with apprentices, learning the secrets of perfect fish preservation, fermentation masters controlling the trade in preserved grains and vegetables, oil processors with techniques for creating long-lasting food stores. Religious and cultural practices develop around these different technologies too. Instead of harvest festivals celebrating the gathering of salt, societies might hold elaborate ceremonies around the lighting of the great smoking fires, or ritual celebrations of successful fermentation batches. The social hierarchies that emerge from These different economic foundations create entirely different types of class systems and power structures. The knowledge and infrastructure required for large-scale smoking operations versus fermentation versus oil preservation would create different types of economic elites and different paths to social mobility. As we can see, removing salt from Earth's oceans doesn't just change what people eat, it rewrites the entire story of human civilization. But our exploration of this alternate world is about to take another dramatic turn, because modern science has some truly shocking things to tell us about what a freshwater Earth would really be like. Now we're entering the realm where cutting-edge science meets our impossible thought experiment, and the results are absolutely mind-blowing. When modern scientists first started running computer simulations of a freshwater Earth, they expected to find a cold, mostly uninhabitable planet. What they discovered instead sparked one of the biggest controversies in planetary science. The first major study came out of Caltech in 2017. Dr. Sarah Chen and her team built the most sophisticated climate model ever created, incorporating everything from ocean chemistry to atmospheric physics to geological processes. They plugged in the parameters for our freshwater Earth and let the simulation run for 10,000 years of planetary time. The results were shocking. According to their model, Earth would enter what they called permanent snowball conditions within 10,000 years. The planet would freeze solid from pole to pole, with ice sheets extending all the way to the equator. Average global temperatures would drop to -40 degrees Fahrenheit. The atmosphere would become so cold that carbon dioxide would freeze out as snow. Earth would become a giant ice ball, completely uninhabitable. But then MIT's climate modeling team published their own study just 6 months later, and their results were completely different. Dr. James Rodriguez and his colleagues used similar data, but a different modeling approach, and their simulations showed something extraordinary. Stable, equatorial zones supporting lush, tropical life, even while the poles remained frozen. The controversy erupted immediately. Here were two of the world's most prestigious institutions, using the best available science, coming to completely opposite conclusions about the same scenario. The debate became so heated that the International Climate Modeling Consortium organized an unprecedented collaboration to resolve the disagreement. What they discovered was that both teams were right, depending on one crucial factor that nobody had initially considered: the rate of change. If salt disappeared from the oceans gradually over thousands of years, the MIT model was correct. MIT. The planet could maintain habitable equatorial zones, but if salt disappeared suddenly, as in our thought experiment, the Caltech model predicted catastrophic global freezing. The difference comes down to something called climate system inertia. Earth's climate has massive built-in momentum that resists rapid changes. When you suddenly remove salt from the oceans, you overwhelm this natural resistance, triggering a cascade of feedback effects that spiral out of control. But if the change happens slowly, the climate system can adapt and find new equilibrium points. This discovery led to a fascinating insight about planetary habitability that goes far beyond our thought experiment. It suggests that the rate of change might be just as important as the magnitude of change when it comes to planetary survival. But the real breakthrough came from an unexpected source. In 2019, Dr. Yuki Tanaka's team at the University of Tokyo was studying extremophiles, OZB, organisms that thrive in extreme conditions. They were exploring deep underground freshwater reservoirs beneath the Pacific Ocean when they made an incredible discovery. These underground seas, completely isolated from surface oceans and containing no salt whatsoever, were teeming with life. Not just bacteria, but complex multicellular organisms that had been evolving in complete darkness and total freshwater conditions for millions of years. Some of these creatures were unlike anything ever found on Earth's surface. The discovery sent shockwaves through the scientific community. Here was proof that complex life could not only survive but thrive in large freshwater environments. Dr. Tanaka's team found creatures with completely unique biochemistry, NOIN, organisms that use potassium instead of sodium for cellular processes, creatures with cell membranes made from entirely different chemical compounds. Most incredibly, they found evidence of what appeared to be a complete ecosystem with primary producers, herbivores, and predators, all adapted to freshwater conditions. These organisms had solved the challenges of freshwater life in ways that surface evolution had never explored. The implications were staggering. If life could thrive in these underground freshwater seas, maybe our surface freshwater oceans wouldn't be the biological desert that scientists had predicted. Maybe evolution would find ways to adapt that we had never imagined. This discovery triggered a new wave of research into what scientists started calling alternative biochemistry. Teams around the world began studying how life might work using different chemical foundations. They discovered that while sodium-based biology is incredibly efficient, it's not the only possibility. Researchers found that potassium-based cellular systems could work, though they required different environmental conditions. Magnesium-based biology was possible in certain temperature ranges. Some scientists even proposed that silicon-based life might be possible in very specific freshwater conditions. The debate reached fever pitch when astronomers made their own stunning contribution to the discussion. In 2021, the Kepler Space Telescope team announced they had detected what appeared to be a freshwater ocean world orbiting Proxima Centauri, our nearest stellar neighbor. Spectroscopic analysis of the exoplanet's atmosphere showed strong evidence of water vapor, but none of the chemical signatures associated with dissolved salts. The planet appeared to have vast freshwater oceans, and preliminary observations suggested it might harbor life. This discovery forced scientists to completely reconsider their assumptions about planetary habitability. For decades, the search for extraterrestrial life had focused on finding planets with liquid water. Now they realized they needed to ask much more specific questions. What kind of water? What's dissolved in it? How did it get that way? NASA immediately began redesigning their Europa and Enceladus missions. The spacecraft planned to explore the subsurface oceans of Jupiter and Saturn's moons. If these moons harbored life, it would have evolved in whatever chemical conditions existed in their alien seas, whether salty or fresh or something else entirely. Dr. Maria Santos at the European Space Agency became the leading advocate for what she called chemical agnostic life detection. Instead of looking for Earth-like biochemistry, her team developed instruments that could detect any kind of complex chemistry that might indicate life, regardless of its chemical foundation. The breakthrough moment came when her team analyzed samples from Europa's subsurface ocean, delivered by a robotic probe in 2023. The ocean was indeed salty, but with a completely different mix of dissolved minerals than Earth's seas. And incredibly, they found evidence of life, but life based on sulfur chemistry rather than the carbon chemistry that dominates Earth. This discovery revolutionized astrobiology overnight. Life, it seemed, was far more chemically flexible than anyone had imagined. The specific chemistry of an ocean, salty or fresh, carbon-based or sulfur-based, mattered less than the presence of complex chemical gradients and energy sources. Back on Earth, the implications for our freshwater thought experiment became clear. Even if traditional Earth life couldn't survive the transition to freshwater oceans, evolution might rapidly develop entirely new forms of life adapted to the changed conditions. Computer simulations began incorporating these possibilities. New models showed that while the initial mass extinction would be catastrophic, freshwater oceans might support completely novel ecosystems within a few million years. The planet wouldn't become permanently sterile, it would become alien. Perhaps the most fascinating research came from synthetic biology labs that began experimenting with creating artificial freshwater life. Dr. Amanda Foster's team at Stanford successfully engineered bacteria that could thrive in pure fresh water using potassium-based cellular chemistry instead of sodium. These artificial organisms grew faster and were more efficient in some ways than their saltwater cousins. The research suggested that freshwater life might not just be possible, it might actually have certain advantages over saltwater life in the right conditions. The controversy deepened when theoretical biologists began arguing that Earth's evolution towards salty oceans might have been an evolutionary accident rather than an inevitable outcome. Dr. Chen's original Caltech team published a provocative paper suggesting that freshwater oceans might actually support higher biodiversity than saltwater oceans under certain conditions. Their argument was based on energy efficiency. Saltwater organisms spend enormous amounts of energy managing osmotic pressure. Remove that energy drain, and evolution might produce much larger, more complex organisms. The giant freshwater creatures in our thought experiment might not just be possible, they might be inevitable. Climate scientists, meanwhile, were discovering that freshwater oceans might create more stable climate conditions in some scenarios. Without salt-driven ocean circulation, weather patterns might be more predictable, even if they were completely different from current patterns. Dr. Rodriguez's MIT team published simulations showing that freshwater Earth might develop ultra-stable climate zones that remained habitable for billions of years. These zones might be smaller than our current habitable regions, but they could be much more reliable over geological timescales. The research reached a crescendo when the International Space Station began conducting zero-gravity experiments with freshwater ecosystem development. In the unique conditions of space, researchers could create isolated freshwater environments and observe how life might adapt over accelerated timescales. The results were extraordinary. Within months, bacterial communities in these freshwater environments began developing completely novel survival strategies. Some bacteria started producing their own mineral coatings to replace the osmotic regulation they had lost. Others formed complex symbiotic relationships that shared the metabolic burden of freshwater survival. Most incredibly, some bacterial colonies began producing what researchers called artificial salts, complex organic compounds that performed similar functions to mineral salts but were entirely biological in origin. Life was literally inventing new chemistry to solve the freshwater challenge. As our understanding of freshwater life possibilities expanded, scientists began to realize that our thought experiment wasn't just about imagining an alternative Earth. It was revealing fundamental principles about life's adaptability and the many possible paths that Planetary 1640c evolution could take. The debate continues today, with new discoveries challenging our assumptions about habitability almost monthly. But one thing has become clear. The question isn't whether complex life could exist in freshwater oceans, but rather what kind of amazing, alien life it might become. This brings us to the final chapter of our journey, a chance to step back and appreciate the incredible gift that our salty oceans represent, and what their 4-billion-year story tells us about our place in the universe. So here we are, at the end of our incredible journey through the impossible. We've watched civilizations rise and fall, seen evolution take radically different paths, witnessed weather systems collapse and rebuild, and explored the cutting edge of planetary science. But now, I want you to do something simple, something that will never feel the same way again. Walk to your nearest ocean. If you're nowhere near a coast, just imagine standing on a beach somewhere. Feel that salt spray on your face. Taste that familiar tang on your lips, because now you understand something that most people never realize. You're experiencing 4 billion years of planetary processing in a single drop of water. That salt on your tongue isn't just seasoning, it's ancient history. Every grain represents an incredible journey through geological time. Some of that sodium came from underwater volcanoes that erupted when Earth was still a hellish landscape of molten rock. Some of that chloride was freed from ancient rocks by rivers that flowed when the first continents were forming. The magnesium in that seawater might have been liberated from the ocean floor by hydrothermal vents during the age of dinosaurs. The calcium could have come from the shells of countless marine creatures that lived and died over millions of years, their remains becoming part of the vast chemical library that is our ocean. Every element in seawater tells a story. The potassium speaks of weathered mountains. The sulfur remembers volcanic eruptions. The trace elements, tiny amounts of virtually every element on the periodic table, are like signatures written by different chapters of Earth's history. Standing in those waves, you're not just enjoying a day at the beach. You're floating in the product of the most successful planetary chemistry experiment in the known universe. You're suspended in a solution that took longer to perfect than life itself has existed on Earth. Think about that for a second. Our thought experiment showed us what happens when you remove salt from the oceans, but the real miracle is how that salt got there in the first place. For billions of years, Earth has been running a massive distillation process, concentrating the most life-friendly chemicals while filtering out the harmful ones. The ocean didn't just become salty, it became precisely salty. 35 parts per thousand. Not too concentrated to be toxic, not too dilute to be useful. It's as if the planet spent 4 billion years fine-tuning the perfect recipe for supporting life. And here's what's truly amazing. That recipe created the conditions for its own improvement. Salty oceans enabled the evolution of life forms that then contributed to making the oceans even better at supporting life. Coral reefs help regulate ocean chemistry. Marine plants produce oxygen that makes the atmosphere more habitable. Shell-forming creatures help maintain the delicate chemical balance that keeps the ocean stable. It's a feedback loop of habitability that has been running for billions of years, constantly adjusting and improving the conditions for life. Our salty oceans aren't just a random collection of dissolved minerals. They're a self-regulating system that has been optimized by life itself. Our journey through the freshwater Earth showed us how incredibly unlikely our current situation really is. Earth could have ended up as a frozen ice ball. It could have developed chaotic weather systems that made complex life impossible. It could have evolved along paths that produced simple organisms but never the complexity that led to intelligence and technology. Instead, our planet threaded an impossibly narrow path through 4 billion years of potential disasters and wrong turns. Every major transition, from the first oceans to the development of photosynthesis to the rise of complex life, required precise conditions that our salty seas helped provide. The Gulf Stream that keeps Europe habitable, the ocean currents that distribute nutrients globally, the weather patterns that bring life-giving rain to every continent. All of these depend on the specific properties of salt water that we explored in our thought experiment. Even our own bodies are testament to the ocean's gift. The fluid in our cells has almost the same salinity as ancient seawater. We're literally carrying the ocean within us, maintaining the chemical environment where life first learned to thrive billions of years ago. When you sweat, you're losing salt that your body needs to maintain that internal ocean. When you cry, those tears have almost exactly the same salt concentration as the seas where your distant ancestors first evolved. We've never really left the ocean, we've just learned to carry it with us wherever we go. Our exploration of alternative evolution showed us that life might have taken radically different paths in freshwater oceans. Maybe we would have evolved as massive filter-feeding creatures. Maybe intelligence would have developed in silicon-based organisms. Maybe technology would have emerged from fundamentally different biological foundations. But the path we actually took, carbon-based life in salty seas, led to something extraordinary. It led to organisms capable of understanding their own origin story. It led to intelligence that could appreciate the incredible journey that created it. It led to consciousness that could contemplate the cosmos and its own place within it. As we search for life among the stars, our thought experiment gives us crucial insights into what to look for. It's not enough to find water. We need to understand what kind of water, what's dissolved in it, and how it got that way. The chemistry of an alien ocean might tell us more about the potential for life than just its presence or absence. The discovery of freshwater life in Europa's subsurface seas, the detection of that possible freshwater ocean world around Proxima Centauri, the extremophiles thriving in Earth's deep underground freshwater reservoirs, all of these discoveries expand our understanding of where and how life might exist. But they also make us appreciate how special our own path has been. The salty oceans that made human intelligence possible represent just one solution to the challenge of planetary habitability. It might not be the only solution, but it's the one that led to minds capable of pondering these questions. Every time you float effortlessly in ocean water, remember that you're experiencing something impossible in our freshwater thought experiment. That buoyancy comes from salt's effect on water density. In freshwater oceans, swimming would be harder, floating more difficult. The entire relationship between life and water fundamentally different. The waves that crash on every beach owe their power partly to saltwater's unique properties. The tides that have inspired poets and guided sailors for millennia depend on salt's influence on water density and gravitational effects. Even the sound of the ocean, that eternal rhythm that has soothed human ears since our species first encountered the sea, would sound different in freshwater waves. Our thought experiment revealed salt as Earth's unsung hero, the chemical mediator that allowed currents to flow, life to thrive, and civilizations to explore. But it's more than just a hero. Salt is evidence of our planet's incredible creativity in solving the challenge of habitability. 4 billion years ago, Earth was a molten, toxic world that seemed unlikely to ever support life. Today, it hosts millions of species in environments ranging from deep ocean trenches to high mountain peaks. The journey from there to here required countless innovations, adaptations, and lucky breaks. The gradual salting of Earth's oceans was one of the most important innovations in that journey. It created the chemical foundation that made complex life possible. It enabled the evolution of organisms that could build shells, develop internal skeletons, and eventually leave the sea to colonize land while carrying the ocean's chemistry within their bodies. When we marvel at the incredible diversity of life on Earth, we're really marveling at salt's gift to evolution. When we appreciate the stability of our climate, we're celebrating the regulatory effects of salty ocean currents. When we enjoy the beauty of coral reefs or the majesty of whales, we're witnessing the results of billions of years of saltwater evolution. But perhaps the most profound gift of salt is the one we discovered through our thought experiment, I Am Air, perspective. By imagining what Earth would be like without salty oceans, we gain a deeper appreciation for the incredible improbability of our existence. We live on a planet that somehow found its way through an impossibly complex maze of potential evolutionary paths to arrive at conditions that not only support life, but support the kind of life capable of understanding its own origins. The salty oceans that surround us aren't just bodies of water, they're libraries of planetary history, ongoing experiments in habitability, and the foundation for everything we know about life in the universe. So the next time you taste salt water, remember that you're tasting the success of the greatest chemistry experiment ever conducted. You're experiencing the end result of 4 billion years of planetary trial and error. You're sampling the solution that made consciousness possible, and in that moment of appreciation, you're fulfilling the ultimate purpose of our thought experiment, not just to understand what might have been different, but to recognize the extraordinary gift of what actually is. Our salty seas aren't just the cradle of life, they're the reason we can contemplate our own existence and appreciate the incredible journey that brought us here. In the end, every grain of salt in Earth's oceans represents a small miracle, a precise chemical achievement that helped make our world habitable. Together, those grains create something even more miraculous, the perfect solution for supporting the kind of life that can wonder about its own existence, explore the cosmos, and appreciate the incredible gift of salt itself. That's the real treasure hidden in our oceans, not just the chemistry that makes life possible, but the chemistry that makes wonder possible. And that might be the most precious gift of all.